So here we have it. Welcome. So last time we were looking at the beginnings of calorimetry, and we said, look, there's really three different types of calorimetry. There's one type of calorimetry which basically has something like a piece of brass going into some water. There are different materials at different temperatures. The heat given up by the brass would be gained by the water, and they form a final temperature. It's still brass and it's still water. It's as simple as that. So we call that calorimetry with no phase change. And then the next complexity is we take two substances which are different forms of the same thing. So the classic example is ice and water. And again, you drop the ice into the water, and the heat lost by the water is gained by the ice. And here, as we did in lab class, you've got to watch out, because you not only have a heating of the ice, but you have a phase change for the ice, and then you have heating of the ice water. So it's more complicated. And then the final version, which sounds even more complicated, but is actually just a slight variation, is if we have two different substances where they undergo a phase change. So the one that in the homeworks and in the old tests, I talk about SIP and GLOP, because I just wanted to, make up two names. And now, I talk more about butter and oil, because it's, I was concerned originally that if you knew the specific heat for butter, you might put the wrong number in. But there is no one knows specific heat for butter. You've got to look it up. So I can get away with it. But the idea is it's more able to visualize it. If I take like a stick of butter and say it is cold, and I drop it into hot water, then what's going to happen is the heat lost by the hot water is gained by the butter, and that is used to heat the butter to its melting temperature, melt the butter, and then heat the melted butter to its final temperature. And so we have a phase change, but the two substances at the end are not the same. It's not like water and water because the ice turns to water. It's butter and oil. So, did I say water before? It's butter and oil. So it's just a slight variation. We've done, last time we did the calculation for the simplest example, where we just have, just wait. The simplest example, because this is basically one substance falling into another, and there's no phase change. Let's now look at things with phase change, and the classic we're going to do is ice and water. So what we have is a 4 kilogram, so that's 4 kilogram, and then it's minus 10 degrees C, and it's a block of ice, and we have 8 kilograms, and it's plus 20 degrees C water. And we've got to show that the equilibrium temperature is 11.6 degrees C, and we're given some information. So we're given the C for ice is equal to 2 joules per kilogram degree C. And sometimes you'll see degree K, because it's the same number. The size of a degree C is the same as the size of a degree K, so it makes no difference. Yes?
It's giving us that C ice, the constant of ice.
Yeah, I'm reading it from there, yeah. And then the next thing we have is that C water is equal to 5 joules per kilogram degree C. And then we have L, which is the specific heat for, and it has CRY, crystallization, solidification, if you like, just different terms for the same thing. And that's 6 joules per kilogram. That's a latent heat, of course. And then we have the latent heat of vaporization, and that equals 14 joules per kilogram. So we're given some background information. And we know that my change in Q is equal to 0. And I need to figure out what's lost and what's gained. And frankly, the most common mistake is people miss out entire terms. So let me show you a way you can avoid missing out entire terms. And that is, we go back to our diagram, where this is, of course, the solid bit. and then there's the melting of the solid, and then this is the liquid bit. And we start off here. And in this case, we're at -10. And then we go to 0 degrees C because that's the melting point of ice. The reason why I put ice in inverted commas is because I'm cheating. The specific heat of ice are not these numbers, but I want to give you a problem with easy numbers. So I can't call it ice because it's not got the right numbers for ice, but it has got numbers I'll give you. So why not call it smudge? Because by saying it's ice with my hands like flicking, it means that you know that the melting point is 0. I don't have to tell you the melting point. It just makes it a bit more accessible. All I'm doing is I'm messing with the specific heats and the latent heats. Okay. So we go to that, and then so a little bit of energy is used to heat the ice to its melting point. Then a little bit more energy is used to melt the ice. And then if there's any energy left over, and there will be, then I've got to heat the ice water to the final temperature. And all of this is paid for by the cooling of the hot water. So can you see how by looking at this diagram, I know mathematically I need to quantify the first step, and I know mathematically I need to quantify the second step, and I know mathematically I need to quantify the third step, and I know mathematically I need to quantify the fourth step. So I need 4 terms. And people will miss a term out. They'll put 3 terms down because they forget they've got to melt the ice. Or they forget that the ice has to be warmed to its melting point. So by looking at this diagram, I just make fewer mistakes.
What's the third step?
This third step?
Yeah.
It's warming up the melted ice, which is now water, to its final temperature. So we heat the ice up until it melts. We melt it. We heat the melted ice water to its final temperature. And if I don't have enough energy, then I won't heat it up that much. But I will not make it, deliberately anyway, where you don't have enough energy to stop the melting of the ice. But that would be a possibility. But I won't do that. I'll always have it that you melt the ice up, you heat the ice up, you melt it, and then you have some energy left over. Okay. So I need terms for this. So I have, well, the first term, the mass of the ice. And then I'm heating it up. So it's a specific heat issue. So I have the specific heat for ice. And then I have the temperature change for the ice. There's my first term. And then I need to melt it. So I have the mass of the ice. And I need the latent heat of crystallization for the ice. I'm going to run out of space. Then I have the mass. Now the ice is melted, but it's still the same mass. So I'm going to call it the mass of the ice because it's now water, but it's still the same mass. Times specific heat, but now it's water, so it's specific heat of water times the temperature change. And to remind me, I'm going to call this ice water. There's my third term. My fourth term is the mass of the hot water times specific heat for water times the temperature change for the hot water equals 0. I'm going to put a...
I do not see where you're getting all of this from.
Well, think about it. Let's go through it. Attend. You know that heat, you know Q is equal to mc delta T because we learned before that C is equal to Q over m delta T. So when you're dealing with the temperature change, you want to use Q equals mc delta T. And you know that Q is equal to ml because we learned before that L is equal to Q over m. So when you're dealing with a phase change, you're going to use that equation. So I've just written down the first equations for that bit because it's a temperature change. Then the second term's the latent heat, which is for that bit because it's a change in phase. The third expression is that bit because it's a temperature change. And the fourth expression is that bit because it's a temperature change. Okay? So, then I say, I'm going to run out of space. So then we say, well, the mass of the ice times the specific heat for the ice. Now let's be a bit more specific about these temperature changes. And you look at your diagram, and you look at the diagram, and you say, which bit am I on? And I am on this bit down here, the first step. And you look and see, what's my final temperature for this step?
0.
So it's 0 minus, and what's my starting temperature for this step? I'm going to call it T ice, so it's generic, so you know, but it's going to be minus 10, yeah. Plus the mass of the ice times the latent heat for ice, plus the mass of the ice. Now it's water, it's melted, so it's the specific heat for water. And again, let's look at this temperature change. So you look at your diagram, and what's the symbol I have for the end of this, the temperature for the end of this step? I don't know its value, but I've got letters for it. I'm on the third step, so what's the temperature I end up at? TF minus 0. And then I have the mass of the hot water times specific heat for the water times, let's look at our temperature changes for this hot water now. What's the final temperature that the hot water ends up at? You don't know the number, but you know the symbol, yeah? And what's the initial temperature? Look at your diagram. Here's the stage I'm looking at. TH. And that equals 0. So look at those terms for temperature and make sure you see that I'm going from there to there. So it's 0 minus T ice. And then in the third stage, I'm going from there to there. So it's TF minus, in this case, 0. And in the fourth step, I'm going from there to there. So it's TF minus TH. So you see where those letters come from. You see what they mean.
Why is the last one TF minus TH, not TH minus TF?
Oh, because what's the final temperature of this part? Doesn't the hot water cool?
Yeah.
So shouldn't the final temperature be lower than the initial temperature? See, you may have been taught to put the gained equals what's heated. That's the way I was taught. Heat lost equals heat gained. When you do it that way, you've got to have positive things on both sides. And so you kind of trained, maybe formally but maybe informally, to always come out with a positive temperature change, because you need a positive temperature change on both sides. So you kind of trained to say, oh, it's T hot minus TH minus TF. But that's not logical. What we train you over and over again is final minus initial. Changes are final minus initial. So why not just, so by saying my delta Q equals 0, and then just adding all these 4 bits together, not putting the heat lost at the other side, it follows through more logically. That's where it comes from. Cool. So put numbers now. It's done. The problem's done, basically. Let's just put some numbers in.
What
So,
does the TH stand for?
well, it's here. It's T hot. It's the hot water that's cooling down. So the mass of the ice is 4, and the specific heat for the ice is 2. And then we have 0 minus 10. And I want to write it like that just so you can see what I'm doing. In a test, I'd probably put minus, make it into a plus. But plus the mass of the ice is 4, and the latent heat of crystallization. I've been a bit sly here. I'm giving you 2 latent heats to see if you know which one to use. We don't actually vaporize anything on this example. So you'd have to use the 6. And that is sometimes called latent heat of solidification, latent heat of crystallization. The other one would be called latent heat of vaporization, typically. Okay.
Why crystallization?
It's just traditional. It kind of like forms into a crystal.
No, I mean, why are we using the crystal one?
Well, are you vaporizing the ice, or are you changing the ice from water to steam, or are you changing it from ice to water?
Is to water?
So you need that one. If you go back, we had latent heat vaporization on the right, and we had latent heat crystallization on the left, and they're not the same thing. Okay, so just review those. So then we say mass of ice. Mass of ice is for, now it's water. It's the ice water. It's still the same amount of stuff, but it's water. So I can't use the 2 for the specific heat. I got to use the 5 for the specific heat. And then I have T final, that's what I want to find out, minus, and in this case, my melting point is 0, so it's T final minus 0, plus. Now I'm looking at the diagram, looking at the hot water, so it's 8 kilograms. And we have the specific heat of the hot water. It's still water, so it's 5. And then I have my temperature change, which is T final minus, and my T initial, if I look at my diagram, is plus 20. And that all equals 0. So there's my 4 terms. As I say, at this point it's sums. 4 2s are 8. 8 times 0 is 0. Minus and minus makes plus. 4 2s are 8. 8 times 10 is 80. Plus. 4 6s are 24. Plus. 4 5s are 20. That's 20 times TF. Minus, plus 0. That's 20 times 0 is 0. Plus 4 5s, 5 8s are 40. 40 TF. Plus minus, I should have put minus in there, doesn't matter. 40 times 20 is 800. Equals 0. Let's pull the TFs to one side. 60 TF. Let's take, let's plus 80 and 24 is 104. 104 minus 800 equals 0. 60 TF is equal to, it's going to be 694 when I take it to the other side. TF is going to equal 1. I've got a problem somewhere. Oh, 60 TF. Yeah, that's right. 696. I am not. I didn't have my breakfast this morning, so that's going to be.
TH20, not 8.
Why is the T hot 20? Look at your diagram. Look at your. Yep. So 6 degrees C. Cool. So 4 steps. How do you know there's 4 steps? Because you look at the diagram or you remember. It's one or the other. But most people, if they make a mistake, the most common mistakes, the most serious common mistake is people forget an entire term. They'll miss out the melting of the ice, or they'll miss out the warming of the ice. They'll miss the entire term. And the
Ice changes from ice to water. It's always going to be 0 degrees Celsius.
ice does, yeah. Now that's why I'm using the term ice. If I used another substance, I'd have to give you that melting point. Another common mistake is people, they just, for this bit here, they'll say, oh, T final, it's T final minus T ice. They're not looking at the diagram. They're not recognizing that that journey ends when you're melting the ice, not at the final temperature of the thing. So they have T final, they have T final, they have T final. It's like a mess. Once people get past those two, you know, if they have the right number of terms and they don't make the mistake about the T final, then they tend to do okay. It's just, yeah, yes.
Why aren't we taking account when they're mixed for like hot water, you know, mass being 12 instead of just 8?
Oh, because if you look at this diagram, the heat that's gained by the cold is lost by the hot, and I've taken into account that heat gained by the ice water there, and so all that's left is the heat lost by the hot water, and there was only 8 kilograms of hot water. Yeah. So I agree in a term there'd be 12 kilograms of stuff at the end, but we've got to do it step by step by step. So it's really, I think it's really important that you get used to drawing the diagram and understanding where this stuff comes from. Otherwise, you're just learning a magic formula, and if I change anything, it's going to be tragic, but, you know. So. Cool. Let's make it a bit more interesting. Please, 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 please. Over there, please. He's distracting me again. So, let's make it a bit more interesting. So, 3 kilograms, 15 degrees C block of butter. So this is 3 kilograms, and it's plus 15 degrees C. Block of butter dropped into a calorimeter. That calorimeter has 10 kilograms, and it's 40 degrees C oil. Show that the equilibrium temperature results in 35.9. I say C for the solid butter is equal to, and I'm making this up, 2 joules per kilogram degree C. And I say the C for the liquid butter is equal to 5 joules per kilogram degree C. And I say the L for the butter. Butter's got to go to liquid butter, so L for the butter is 6 joules per kilogram, and C for the oil is equal to 7 joules per kilogram degree C, and then the final little bit, the melting point, because it's not ice, for butter is 20 degrees C. So I didn't give you 2 latent heats this time. I gave you the one you're going to use. I could have given you 2, but I gave you just one of them. But you've got this added complication now in that you've got a different melting point, and you've got different substances when it's all melted. It's not all water. So the diagrams are a bit harder because it's not the same diagram. But what we have is we have the heat that's gained by one is lost by the other. And the way this is going to go is it's going to go like that, it's going to go like that, it's going to go like that for the butter. And we're going to have 3 little bits to it, just like before. And then for the oil basically is down here, and the oil is like that. So this is T final, because the oil ends up at the T final, and this is T final. So it's not an easy diagram to draw. Okay, so sometimes I cheat and I pretend it's ice, and I draw it in the same diagram, but it's not really the same diagram. What I say is my change in heat for my system is equal to 0. So I look at my top diagram and I say, oh, I've got to heat the butter up to its melting point. So I have the mass of the butter times the specific heat for solid butter times the temperature change for my solid butter. That's that little guy there. I've just taken my cold butter and I've worked out how much energy I need to make it at its melting point. Then I've got to melt it. So I have the mass of the butter, because it's still the same amount of butter, and I have the latent heat for the butter, because I've got to melt it. That's that guy done. And then I have the mass of the butter times the specific heat. It's the specific heat now for liquid butter, because it's melted.
What's SP?
Solid butter. And I'm going to do the temperature change now for the liquid butter, which is there. Got one more term. The mass of the oil times the specific heat for the oil times the temperature change for the oil equals 0.
So what he's saying is after the butter is melted, it became oil?
No, not at all. I'm saying that that fell into there and it melted and became warm butter. Warm liquid butter. So this is still in there. So this is the term for heating the solid butter to its melting point. This is the term for melting it. This is the term for warming up the liquid butter. And that's paid for by the cooling of the oil. Okay? So in the end, I don't have oil in oil or butter and butter. I have liquid butter in liquid oil. So it's not like the ice in the water where it becomes the same thing. So now, if I look over here, let's be a bit more specific about my temperatures. The mass of the butter times the specific heat for the solid butter. My temperature change for the solid butter, it's going to be the melting point minus T solid butter cold. I'm running out of symbols. Plus the mass of the butter times the latent heat of the butter. And then we have the mass of the butter times the specific heat for the liquid butter. And now, when I look at my temperatures for that, I got T final, because that's where I end up at, minus minus melting point. What was the final temperature in the first step becomes the initial temperature in the third step, because we go from the melting point upwards. And then this is plus the mass of the oil times the specific heat for the oil times T final minus T oil hot equals 0. I'm running out of space again. Got a question?
What's the third term?
This guy here?
No, back a little bit.
There?
From the first delta T, what it breaks down to?
T solid butter, which is cold.
And your one behind it?
The one behind it, melting point.
Oh, melting point.
Yeah. So now let's put some of these temperatures on my diagram so you can get a better view where it comes from. It says 3 kilograms of butter at 15 degrees C, so this is 15. There. And it melts at 20 degrees. So that's 20 there. And that's my T final. And then up here, I have my T oil hot, which according to this is 40 degrees. So just take a minute and see if you're okay with where those temperatures are written down in my question. I had the temperature of the butter initially, which was at 15. I have the melting temperature, which is 20. And then I go to the final temperature. And then I have the temperature of the oil initially, which is 40, and that goes to the melting temperature. Yep. Rest is numbers. So 3 times the specific heat for solid butter is 2 times the melting point. My melting point is 20 minus 15. Because I started off at 15 and I ended at 20. Plus the mass of the butter, which is 3, times the latent heat for the butter is 6. Plus the mass of the butter is 3. The specific heat for liquid butter is 5. And then I have my T final, which is what I want, minus my melting temperature, which is 20. Plus. Now I'm looking at the oil. The mass of the oil, 10, times the specific heat for oil is 7, times my temperature change, T final, minus, and the oil started at 40 degrees. So look at those numbers. I have my first term, starts at 15, ends at 20. I have my second term, it's melting. My third term starts at 20, ends at TF. My fourth term's for the oil, starts at 40, ends at TF. Six times 20, 120. Oh no, let's do that. Let's make my life easier. 6 times 5 plus, let's just do it. 6 times 5 is 30 plus 18 plus 15 TF minus 300 plus 70 TF minus 2,800. 7 fours are 28 and there's 2 zeros in there. 2,800 equals 0. So, get my TFs together. So that's 85 TF. Get my numbers together. 30, 48. Let's put my negatives together. 300, 3,100 equals 0. 85 TF is equal to, not 3,100, 2,000. I need to do the, I'm not good at doing this in my head. 3,052. 52. Thank you. So TF is going to equal 3,052 divided by 85. 35.9. 35.9.
Wasn't it the original temperature?
That's the temperature I ask you to prove. That won't be there in the test. No, I'm not being flippant. It's just that So I used to just have the questions just like in the test, and then I couldn't remember what the answer was. It's been a year since I wrote it, and you didn't know what the answer was. So sometimes if I made a mistake, it wouldn't show up. And I wouldn't stop and correct it, and so people would have a mistake, and it happens. People have slips. But they're learning a slip. So then I started putting the answer in, and I thought I'd be cute, and I'd say, prove that. But then it makes the question sound differently from what it will sound in the test. So what I'm going to go to is eventually I'll rewrite these, and I'll put down the answer at the bottom so that we can all see the answer, but it's not part of the question. So I really regret doing that. I'm glad I got the answer on there, but I regret writing it like that. I was just being cute. It was like I thought, oh, this will be really slick. And like most things like that, it don't work. You know. Three different. So let me point something out to you, okay? You might be like, oh my word, three completely different things. I want to show you something. If I look at this example, the only difference between this example and the previous example, there's two differences. One is that the melting point was not 0. So rather, in the previous one I had 0 here, and I had 0 there. All right, it's just a different melting point. What the heck? And the only other difference was that in the previous one, because I ended up with ice water in water, that specific heat value there and that specific heat value there were the same. If you look back at the previous example, you'll see that it's the same layout. It's just that I have the same value for the specific heat in term 3 and term 4 because they're all water by that stage. And now I have two different values for specific heat. And the only other difference is that in the previous example, my melting point was 0 and now it's 20 degrees. They're the only two differences, yes.
Do you want us to graph two graphs if the materials or like the subsystems are different?
In truth, I would love it if you were to graph the two graphs like that. If you were to do a one graph and use it, I'd also love it because it's a cheat, but it's better than nothing. If you have no graph, it's not like I'm going to grade you down for it, but if you get confused in the number of terms, I'm going to write on your paper, you missed a term, you needed a diagram, you know. So, because that's the way you avoid losing a term. But I don't want you to get the graph right and the question wrong, you know, because it's all about the question.
Get any points for
No, you don't get any points. Because then we started talking about, well, it's a nice graph, well, a not so nice graph, and I only missed out 3 things, and I never grade them. I'll be worried about them when you guys are retired. I'll be still sat there somewhere saying, maybe an extra 1/10 of a point. So I like to keep it simple.
Yeah, you would have passed with the extra 10th.
Right on the edge, and man, forget it. Okay, we're a bit behind, so I'm gonna zoom. If I can. So let's have a look. Oh, that's not 58, is it? No, 38. Okay. So next, draw a bit of a line. There will be a calorimetry question on there of some kind. Probably, anyway. I'm trying to make the test a little bit shorter, but probably. Yes, I know. So first law of thermodynamics. This is all about internal energy. Internal energy is the sum of all the energies of the particles inside your solid, inside your system, reference to the system. Yeah. And there's two ways of getting energy into or out of that system. And one is you can do work on it. I can rub my hands together, and the internal energy of my skin increases. My temperature, therefore, goes up, and I can feel it. Or I can use heat. I can put my hand in a flame, and internal energy of my hand will go up, and its temperature will therefore go up. I could also put an ice pack on my hand and take energy away. And it's not obvious from my hand analogy, but I could actually get my hand to do work somehow. It's actually expanding the gas, and energy leaves. A really good analogy is your bank account. Let's go back to a pen. If you have a bank account, most people in their bank accounts, they have the ability to put money in or take money out via an ATM, or they can go inside the bank and talk to somebody inside the bank and ask them to put money in or take money out. So just a little slice of life. ATMs had just come in Britain when I was there, and the banks were trying to, they were a new technology. So the banks in Britain wanted you to use the ATM because you didn't need to employ somebody for the ATM. So if you use the ATM, it was a feeless transaction. But if you went in and spoke to the teller, that was a little fee, but they'd always charge you for doing transactions over the counter. And I came to the States and found that if you went and spoke to the teller, even if you were long-winded, they didn't charge you anything, apart from there were some bank fees. But they didn't worry about it. Whereas if you used the teller, whereas if you use the ATM, they'd charge you for it. So a completely different business model in the two countries. Same technology, different business model. And for the longest time, I didn't know, this shows my lifestyle, for the longest time, I didn't know that you could actually put money in at an ATM. I thought it was like a one-way valve, but apparently you could put dollar bills in and it would credit it to your bank account, which I have never done in my life. I have never put money in. Let's say that you were dealing with a buddy, and they said, I don't know what happened. I put $5 in at the window, and here's the window teller to prove it, and somehow my balance went down by $45. This is a mystery. I put $5 in at the window, and here's the person, and somehow my bank account went down by $45. The bank must have made a mistake. What do you know really happened? I put $5 in at the window, and then what did I do? I went to the ATM, and I drew out $50, because there's two ways in and out. And you would not kind of go, oh, that's amazing, you know. You'd go, yeah, did you use the ATM? Well, yes. Well, that also takes money now. And yet, if I put a Bunsen burner on a piece of gas, and yet maybe I put 5 joules of energy into my piece of gas using a Bunsen burner, but I expand the gas, making it do 50 joules of energy. People are sometimes amazed that your internal energy goes down, even though you put 5 in and took 50 out, because the temperature goes down. Internal energy is reflected in temperature. So I cool the gas, but I got a Bunsen burner. How can I cool the gas when I have a Bunsen burner? Because it can also do work. So, I mean, I'm speaking from bitter experience, because I remember being mystified by that when I was a student. And it's basically, there's 2 ways in and out. You can have the gas do work. You can have the gas, you can do work on the gas. You can heat the gas. You can cool the gas. Both of those things have to be taken into account. Yes.
Okay. I don't know if this is going to make sense. Maybe just in my head. But with heat, you can put in and out, right? Because you can cool it down or heat it up.
Yeah, you can use an ice pack, or you can use a Bunsen burner.
But
Yeah.
with work?
Oh, yeah. No, the gas can expand, and it will cool. It will take energy out of the system, yeah.
Okay.
So are you squishing the bicycle pump, or is the classic case is if you get a propellant, one of those oil cans where you can, like WD-40, and you can spray it. Not the pump one, but the one where it's got high pressure and you go and it comes spraying out. Or one of those air horns. You know those air horns like people use when they go to football games and stuff like that? If you run that for a long time, it chills. It cools like crazy, because the gas is doing work on the environment. It's reducing the internal energy of the gas. the heat from the room can't keep up with it, so the temperature plummets. So yeah, you can, both ways. It's both ways. One's more obvious than the other, but both ways, yeah. So we say internal energy of a system can be changed by inputting or removing heat and work, and the same thing goes through a bank account. You can steer your way around. So what happens next is, and again, this is another thing that I really struggled with, and that is, so solids don't show the effect of work so obviously. So we tend to talk about gases because they show it very well because it's compressible and not compressible. So then we start talking about gases and we talk about pressure volume relationships. And they'll show you, they'll say, oh, look, you're starting off at the same pressure and volume in each case. That's the same physical state for the gas. And you're ending up at the same volume and pressure in each case, which is the same physical state of the gas, but you're using 3 different routes to get there. And these paths are different. And you got to recognize that when they do a PV diagram, they are drawing a PVT diagram. Boyle's law says that PV equals a constant for a constant temperature. Inverse equals a constant for constant temperature. Well, maybe I started off at a higher temperature. Maybe I started off at a higher temperature still. Maybe I started off at a higher temperature still. Maybe started off. So this is T low and this is T high. And they never draw them on your diagram. And I remember when it finally dawned on me. Because they'll say things like, oh yeah, between this point here at the top and this point there at the bottom, cooling takes place. And I'd be looking all over the question for saying, where does it say cooling takes place? Where does it say the temperature decreases? And they're getting it from the fact that they're imagining a whole series of isothermal lines on here that they're just not talking about. And so, yeah, clearly you're going from a T hot to a T cold. It's obvious from that diagram. And so 2 things came to mind. One was, because I'd spent hours trying to figure this out, and the first thing that came to mind was, wow, why didn't they say that? And I'm sure buried in the text somewhere it was. And secondly, well, why don't you just draw your diagrams with isotherms on them? Because it seems to me they're important. And the idea is, if we don't tell you about the isotherms, we'll find out if you know the isotherms exist. So it's one of those deliberate teacher type things where I'm not going to tell you the whole story to see if you know the whole story. So they miss them out on purpose. It's not like they couldn't afford the ink. It's that, let's see if they know what's going on. So whenever you see a PV diagram, draw the isotherms on. Don't make the mistake I made. So we see on this first one, let me just clean this up a little bit. Well, no, I'll leave it on for a minute. So we see on this first one, we start off with a high pressure, low volume gas. Imagine a syringe of gas, high pressure, low volume. And then we basically get it to reduce its pressure without changing its volume by putting an ice pack around it. We're simply taking heat out of the system, and the thing is, pressure's falling because there's less energy in the system. And then we get the thing to go at constant pressure by, yeah, we're heating the gas, and the gas is expanding. But we're doing it a specific way. So we're changing the volume, and incidentally, the temperature is changing. Maybe we're doing it on purpose, maybe we're doing it. If we just expanded this gas, if we just pulled on the expansion, that's the pressure I would end up at. So the fact that I'm not ending up at that pressure means I must have heated to get it to the pressure I want. In this next one, all I'm doing is I'm expanding the gas, and I'm letting the energy come in from the outside to maintain the temperature. So I'm heating the gas from the outside, but I'm doing it just to maintain the temperature. And in this one, what I do here is, let's think about my isotherms. In this one, okay, I am expanding the gas, and normally if I expand the gas, the temperature would go like that. The pressure would go like that. So I'm heating while I'm expanding to get to that point. And then all I'm doing is I'm cooling the gas. I'm just keeping the volume the same and the pressure's going to fall. Yes?
And the second one is temperature constant then?
That's an isotherm, so temperature's constant. Yeah, that's the intent. So 3 different journeys. I went from Chicago to Tampa by flying south and then flying east. I went from Chicago to Tampa by following the jet stream. I went from Chicago to Tampa by flying east and then flying south. It turns out that just as work is equal to the integral of f dx, if you think about it, it also equals the integral of p dv. Whoa, hold on. Force per unit area is pressure. Volume is distance times area. So I'm multiplying by area on the top to get the volume, and I'm dividing by area underneath to get the pressure. So I've not changed anything. The dimensions are still the same, but it's an equivalent equation. Okay with that? Remember, it's not VdP, it's PdV. And on this diagram, that means that the work done is the area under the graph. And you can see that there are 3 different amounts of area under the graph. And that means that 3 different amounts of work was done on the gas. A little bit, a bit more, a lot. And they go, this is the common scenario, they go, hold on, I started at the same physical state in each case, and I ended at the same physical state in each case, and yet, in these 3 different journeys, I had 3 different amounts of work were done. How can that be? And the answer is, yeah, because it's not just dependent upon work. It's also dependent upon heat. And I did a little bit of work here, but I made up for it in heat. And I did a bit more work here, and I didn't make up for it in heat, and as much. And I did more work here, and I actually took heat out. So it's games. We're back here. Oh man, I took $5 out from the teller, and I put $5 in, and my bank account went down. How can that be? It's like pretending not to know there's an ATM. The same goes for this. We're pretending not to know that there's also heat involved in this. So don't get fooled by it, okay? So we have to take into account how heat and work collectively affect my internal energy. And I have to remember that internal energy is reflected in, it's not equal to, it's reflected in temperature. So if my internal energy increases, my temperature increases. If my internal energy decreases, my temperature decreases. Not 1-to-1, but it happens. Now, I have a little, okay. So let's do this bit first. So work is equal to the integral of P dV. 3 different diagrams. How much work is done by the gas in this expansion? So here I've got I give you the P's and I give you the V's. And can you have a go at that, please? We'll just have a go at this one, just so that we use the clickers one time. If you got clickers, half of you do. So how much work is done by the gas in this expansion? Ooh. So I'm going to stop you like in a minute because I'm running out of time. So keep on. I'll give you until 60, 1 minute. See if you can get it in that time. Let's do that. And then let's see what people say. Mainly C with a little bit of D. So let's have a look and see what's going on here. Well, my work done is equal to the integral of P dV, which equals the area under a PV diagram. So there's the area I'm interested in. It's a rectangle, so work is equal to my pressure, it's constant pressure, which is nice, 5, times my change in area, my change in volume, and it's 4 minus 1, so that equals 5 times 3, which equals 15 joules. So it's not taking just the 5 times the 4 and getting 20. It's got to be the change in the area. Okay.
So you just area under PV1?
Under PV diagram. Yeah. Okay. In the next one, we're going to go work is equal to integral of P dV, which equals, and my pressure I give you somewhere. Where did I see it? Oh yeah, my pressure equals 6 over V squared, the integral of that. I'm going to stop this. So we just did this while you were off air, and basically we integrated it. We basically just used integration to find it. I made a little slip at the end where I just did my math wrong, which is always a reason why you write things down so you can check it. And then we got the answer of 4.5 joules. Let's stop there.